All right. Thank you very much. Thanks for inviting me. It's fun to be here. So I hope you can see my screen by now, and you can also see my mouse. The talk will be about building an error-corrected superconducting quantum processor. On this title slide, you already see a picture of the device that will be the main actor in this presentation. It's a device with 7 qubits on it, and the qubits are the yellow structures, the yellow turtle-like structures that you see here. And I'll explain it in a minute a bit more in detail. So also in my talk, I'll try to do a mix of presenting a relatively recent experiment that we've done towards realizing error correction in superconducting circuits. And it's, I think, a state-of-the-art experiment making a step towards realizing the surface code in superconducting circuits. But since many of you listening to this presentation are likely not experts in superconducting circuits, maybe nor in quantum information processing, I'll spend some time in giving you an introduction to, in particular, superconducting circuits and how to investigate the quantum physics of these systems. The work that I'll be presenting is done by a team of students and postdocs at ETH, and the current team is listed at the bottom of this first slide here. The experiment that I'll focus on is one that was led by a postdoc, Christian Andersen, and done together with a larger team of other postdocs and graduate students, but maybe two that I want to single out is Ans Rem and Stefania Lazar, who played important roles in this experiment. Okay, so maybe let's have a closer look as an introduction to this device that we'll be looking at experimentally throughout this presentation. So this here is a chip, the chip that we've actually done the experiment on. It's about 7 by 14 millimeters in size, so it's 7 millimeters high, 14 millimeters long. As I said, the yellow structures are the qubits, so there are 7 qubits on this chip organized in this double diamond structure that you roughly see here. The qubits can be coupled to their nearest neighbors through microwave frequency resonators, so these turquoise lines here are coplanar waveguide resonators, and they couple neighboring qubits to each other in the topology that you see here. Then every qubit can be controlled through a line that allows you to drive microwave frequency transitions in the qubit, and the purple or pinkish line that you see here is used to apply microwave pulses to the qubit, and a green line is used to apply short current pulses to the qubit that you can use to tune the transition frequency of the qubit on nanosecond timescales. And then every single qubit is coupled to another microwave frequency resonator that is shown in red here. And this microwave frequency resonator can be used to read out the state of the qubit. And one special aspect about this chip is that there is some multiplexing in the readout of the qubit state. And the readout is very fast and also non-destructive on other qubits, and that's important for realizing elements in the surface code. And it's also a, sort of a special feature that was developed in our lab throughout the past few years. So I hope that at the end of this talk you understand a little bit about this type of device, what the elements are, how you operate it, and how you can do an error detection. How you can do the error detection part of the surface code on this very simple 7-qubit device. Okay, so I mentioned to you that there's a number of people currently contributing to the work in our lab, but the lab at ETH existed since 2006 when I moved from Yale to Zurich. And since then, quite a number of students and postdocs have contributed, and here you see those students and postdocs from our lab that have left by now and where they moved on to. And it's nice to see that many of them were able to stay in academia, and there's quite a few that actually now run their own academic groups at a number of different places throughout the world. And I also acknowledge collaborations with many partners, and since there's too many to list overall, I just list the ones of the last 5 years here. Good. So we're talking about quantum error correction in this presentation, and if you're interested in quantum physics in general, then you probably have heard about the quantum supremacy experiment done by Google towards the end of last year. So that experiment was a very nice one. It included a chip with 54 qubits on it, out of which 53 worked. And they were able, and the qubits are shown here as the blue crosses in this very schematic diagram. They were able to control the states of each individual qubit with fidelities of about 1%, or with errors limited by about 1%. They were able to perform good 2-qubit operations on these devices, and they were also able to perform good readout of their qubits. And so then they used this large device here with 53 qubits, which is one of the largest ones that is actually operated successfully at this stage, to implement a random gate sequence on this device. And the gate sequence had a depth of about 20 steps, during which they operated gates between each and every pair of qubits. And this random gate sequence results in a very complicated multi-qubit entangled state. And to reproduce that entangled state or predict what it would be on a classical computer is very computationally intensive. And their goal was actually to use their quantum chip to demonstrate that they can calculate a quantum state that would be very hard to simulate on a classical computer. That would bring even the largest supercomputers to their knees. And even while there is a discussion in the community still about by how much this Google experiment really exceeded the capabilities of conventional computers, I think it's pretty clear that with this type of approach, you can, when adding a small number of extra qubits, possibly outperform, for this particular toy problem, any conventional computing system. But what is also important is, if you look at the ability of this large system here to create the state that it intended to create, namely a 53-qubit entangled state, after these many steps, after this large number of gates, if I remember correctly, there were a few thousand gates operated on this device to reach the final state. The final state had a fidelity of only about 10 to the minus 3 relative to the ideal fidelity of 1 that you would like to achieve. And the reason for that is that the qubits on this device still had finite coherence. Yeah, their coherences were less than 100 microseconds. And also the fidelities with which you could do both single and 2-qubit operations were limited to sort of on the order of errors of 10 to the minus 3 about. And so what this points at is that if you want to build a large-scale quantum computer, you have to deal with these errors, both errors that come from decoherence and errors that come from finite gate fidelities. And one of the ways how to deal with these errors is to use schemes for error correction. And one path into that direction is to implement an error correction scheme. And what you see here is a device, or a sketch of a potential device in which one could encode a logical qubit in many physical qubits. So the idea there is, rather than working with a single qubit that might suffer from a decoherence and then lose its quantum mechanical state, you would distribute the quantum information of that single qubit over a much larger set of qubits and encode that information cleverly over that larger set of qubits. And then try to perform measurements on these qubits that would tell you whether an error occurred on any one of the qubits that you used for these encoding. And like in this picture that you see on the right-hand side, all the red qubits, there's 25 of them in this picture, are so-called data qubits, in which you would encode the quantum information fault-tolerantly. And all the blue and green qubits are so-called ancilla qubits that you would use to try to figure out whether an error had occurred on any of the physical data qubits shown in red. And I'll explain how that process would work and how it's envisaged, and our experiment shows some important aspects of that, or demonstrates some important aspects of that process. Good, and you'll hear more from me about that. Before we go into the details of error correction, I will spend some time of telling you a little bit about superconducting circuits and the physics of superconducting circuits. So what we're essentially trying to do is we're building electronic circuits that behave quantum mechanically from basic circuit elements like capacitors, inductors, and maybe we would think about choosing resistors if we had a use for them. And we're trying to combine these circuit elements in a fashion that allows us to look at the quantum physical properties of such a circuit. And maybe while it's very simplified, I think this is an interesting way to look at how you can think about quantum physics of superconducting circuits. We'll consider two very, very basic examples. You could, for example, consider this capacitor here and a charge on that capacitor, for example, an electron. And classically, that charge could be either on the lower capacitor plate or on the upper capacitor plate. But quantum mechanics would allow for this microscopic particle, the electron on that capacitor, to be in a superposition of being on the upper or lower plate of that capacitor. And quantum mechanically, you could write that as this pictorial wave function where you consider this as a coherent superposition of that single charge being on the lower capacitor plate or being on the upper capacitor plate. And if you believe in quantum physics, for microscopic particles, I think this should be nothing that should surprise you. An aspect that is maybe already a little bit more surprising is that you could consider an inductor enclosed in a loop like such. And then you can consider a current maybe of several billions of electrons circulating through that loop. And that current could either flow clockwise, as is shown here, or counterclockwise through that loop. And quantum mechanics actually does allow the current to be in a superposition of flowing clockwise or counterclockwise, which already sounds a little bit less intuitive, because now this is a macroscopic current being in a superposition of flowing in two ways. But again, you could write that in this pictorial wave function representation. And so one way how to think about how these electronic circuits behave quantum mechanically that I like very much is the following one. So all of you, when you first learned about quantum physics in your introductory physics courses, you've probably learned about particles moving in potentials. And there you understood that position and momentum of particles moving in free space or maybe interacting with some other element that would provide a potential are conjugate variables that describe the dynamics of that particle. In a similar way, in electronic circuits, the charge Q, like the charge of an electron on a capacitor, or the flux phi, that is the flux that is current, the magnetic flux that is generated by a current flowing through such a loop, are similar conjugate variables as position and momentum for particles in free space. And so now, if you remember your introductory quantum physics course, you have then first written down the Hamiltonian for the particle moving in free space, and then you have promoted these conjugate variables to operators, which would give you a Hamiltonian operator. And then for this Hamiltonian operator, you've solved the Schrödinger equation to find the energy levels of that system. And similarly, you can go ahead and write down the full energy of an electronic circuit, express it in the conjugate variable charge and flux, and then promote these charge and flux conjugate variables to conjugate operators, and then solve the Schrödinger equation for that Hamiltonian operator. And that's what you can do for any electronic circuit. Okay, charge and flux are conjugate variables, and thus there is a commutation relation between them that would also then enforce a certain Heisenberg uncertainty relation between flux and charge in a similar way as it's enforced for position and momentum. And so in this way, you can understand how you can in principle take any electronic circuit and look at the quantum physics of it. And what we'll look at a little bit is to understand what conditions you need to fulfill to actually be able to observe the quantum physics in these devices. Okay, so then usually you don't use just capacitors and inductors in these circuits, but you combine them in slightly, but only a slightly more complicated fashion. So one very typical combination of circuit elements is, for example, a parallel or series combination of an inductor and a capacitor that you see here. So in this parallel combination, we'll create a harmonic oscillator. There could be charges on this capacitor, and when the charges flow from one capacitor plate to the other capacitor plate, they create a current through the inductor, and that current creates a flux. And you can write down the total energy of that circuit as the sum of the magnetic energy in the inductor and the electric energy across the capacitor. And that will be quadratic in both the flux and the charge. So you have a Hamiltonian that is representative of a harmonic oscillator Hamiltonian. And that we know how to quantize, and you would know that such a circuit then has a harmonic oscillator Hamiltonian that is written down here, which you could then represent the energy levels as this ladder of states that are equidistantly spaced from each other. And the spacing is exactly given by Planck's constant multiplied by the transition frequency between the levels, which corresponds to the resonance frequency of this resonant circuit, which is given by 1 over the square root of the inductance times the capacitance. And so this is a way how to think about creating electronic versions of photons in electronic circuits. Another very important element in superconducting circuits is one where you replace this linear inductor by a nonlinear circuit element. And this nonlinear circuit element is a Josephson tunnel junction. That's an element where two superconducting metals are brought into contact through a small tunnel junction or through a small tunnel barrier. And this small tunnel barrier then induces the Josephson effect in this device. And a Josephson tunnel junction you can look at as an ideal nonlinear inductor. And how you can think about that, I'll tell you in a second. So here's the equation for the harmonic oscillator Hamiltonian when the oscillator is linear. When the oscillator is nonlinear, you can approximate the Hamiltonian in the following form, where beyond the term that gives you the first order transition frequency, there is an additional term that you need to consider if you try to add a second photon on this nonlinear oscillator. And here on the right hand side you see the energy level spectrum for such a situation, where now the ground to first excited state transition frequency is a little bit larger than the first to second excited state transition frequency. And that would then even be a little bit larger than the second to third excited state transition frequency. And you can model that by this Hamiltonian here. So how can one understand these energy level diagrams, maybe in a bit more of a pictorial fashion that you see on this next slide? So one of the ways how to think about this harmonic oscillator circuit in electronics is to consider the flux phi like a spatial coordinate, and the energy that is stored in the magnetic field is then quadratic in this flux phi. And you can think about the dynamics of the system as a particle moving in this quadratic potential. And the potential is quadratic in this flux variable phi if the oscillator is harmonic. In this case, both the electric energy term in the Hamiltonian and the magnetic energy term are quadratic in Q and phi. When you now enter a Josephson tunnel junction in place of a linear inductor into that circuit, this Josephson tunnel junction has a Hamiltonian that is cosinusoidal in this flux variable phi. So instead of having a quadratic potential, you now have a cosinusoidal potential. And when you solve for the energy eigenstates in this cosinusoidal potential, you find that there's a ground state and then a first excited state. And then you find this unharmonicity that I mentioned to you before, that the first to second excited state transition frequency is a little bit smaller than the ground to first excited state transition frequency. And you understand why that is, because the potential opens up to higher energies, and the energy levels get closer and closer to each other. So the potential on the left-hand side you can use to store photons in electronic circuits. The ones on the right-hand side you can use to identify qubits or atom-like structures in electronic circuits, because here you can now drive transitions that are targeted between different levels here, because the transition frequency between the different levels are non-equivalent from each other, while on the left-hand side for the harmonic oscillator, all the transitions between any of the levels occur at the same frequency. Okay, then let's look at a few examples of harmonic oscillators. So on this next slide, there's examples of harmonic oscillators. You could either make lumped element harmonic oscillators. So here's one way to do that on a chip. there is this meandering line as an inductor. You just make a long wire and that has some inductance. And on the right-hand side of this little circuit, there's a interdigitated capacitor. So there's fingers that, like two combs, face each other, and that creates capacitance between circuit elements. So that's an LC oscillator, just like the one that I've shown to you on the last slide. Then you can make harmonic oscillators also by just carving holes into metal blocks that you see here, an aluminum block in which a cutout is drilled into, and that will have standing waves inside, whose modes you can then describe as harmonic oscillators. Or you can do this thing that we started in 2004, is use coplanar waveguide resonators to create harmonic oscillators and use their quantum physics, or explore their quantum physics in this context of circuit QED, which I'll introduce in a second. Or you could also use systems with one very large Josephson junction, in which case you still have this cosinusoidal potential, but if the potential is deep, so there's a large difference between the bottom of the potential and the top of it, the states which are at the bottom of the potential are approximately equidistant from each other. So that could also mimic a harmonic oscillator for low energies. Then these superconducting qubits that I've mentioned, they really make use of this cosinusoidal nonlinearity of the Josephson junction. And there's very many types of qubits that you can build by combining inductors, capacitors, and these Josephson junctions with each other. And actually people have invented names for those. And here's one that's called the Cooper pair box. Then there's one which is called the transmon. There's one which is called the xmon. And here's one like with one of our graduate students some years ago called the jellymon. Yeah? So that we never used in a publication, but since you make up quantum circuits that have specific energy level diagrams, you can feel a little bit like a chemist discovering new elements and give names to things with new Hamiltonians or with new features in the energy level diagram. And on the next slide, you see a few more of these superconducting qubits that were made but in different labs throughout the past years. And so maybe if you're in the field or so and have been following it a bit, we could take a little quiz and see whether you recognize any of these qubits and what papers they come from. Yeah, some of these are really famous, and maybe you can think about it and figure it out later, maybe as an exercise if you want, or in the discussion. Okay, so what do you do now that you can make these qubits and harmonic oscillators? You can ask yourself how you take these elements and operate them quantum mechanically. And so here's such an element, such a superconducting artificial atom that I mentioned, created from a Josephson tunnel junction and a capacitor. And to do experiments with it, you act in a similar way as you would do experiments with a single atom. If you were doing quantum experiments with a single atom, you would take a laser and shine it on that single atom, maybe at resonance with a transition. And instead of taking a laser, we take a microwave source and connect it through a capacitor to our quantum circuit. And then with your laser and the atom, you would look at the light scattered from the atom. And this we do by connecting another capacitor to our quantum circuit, catching the radiation and then amplifying it enough so that we can detect it, say, with an oscilloscope at room temperature. Okay, so which steps would you need to follow to make sure that this quantum circuit behaves quantum mechanically? So here's the recipe. So the first part of the recipe is to avoid dissipation. So try not to use resistors in your circuit. Make all the circuit elements out of superconductors, because if there's resistance, you will have dissipation, and any energy stored in that circuit, whether you look at the quantum regime or the classical regime, will be dissipated in that resistor. And that dissipation leads to energy relaxation in your quantum system. So that's step one. Step two is that if you were to operate such a circuit at room temperature, say a resonance circuit with 10 gigahertz transition frequency or resonance frequency at room temperature, this would be in a highly excited thermal state. So 10 gigahertz corresponds to about half a Kelvin of thermal energy. And if you're at 300 Kelvin, you're just in a very highly excited state, yeah? Not even considering that your circuit would not be superconducting. So to bring this circuit to the ground state, what you do is you take your electronics and you cool it all down in a cryogenic system close to the absolute zero of temperature, say to 10 millikelvin or so. And at 10 millikelvin is then much smaller than 500 millikelvin, the characteristic temperature. of a transition in your circuit, and then you will just be in the ground state. And a third most important aspect is then that you need to consider what the coupling of your experimental control and detection equipment does to the coherence of your quantum circuit. If that coupling is too strong, the coherence might suffer, but you can control the coupling by, for example, changing the size of this capacitor through which you couple your control electronics and your readout electronics to your quantum circuit. And to really understand that coupling is a prerequisite to preserve the coherence of your quantum bit or quantum circuit that you would like to investigate. And when you follow these three simple steps in this recipe, you can just more or less take any quantum circuit and make and have yourself look at its quantum physics. Okay, so how easy or hard is that these days? So here's even more pictures of qubits. And now I would estimate that there are several hundreds of labs worldwide that academically do research on these quantum circuits, for exploring quantum optics or hybrid quantum systems or even quantum information processing. What is maybe special in the recent years is that more and more industry and also startups get interested in building these circuits. So here you see pictures from Google and IBM and Intel and also Rigetti that are mostly interested in using these circuits to eventually build quantum computers. And this has now made this field very dynamic because now there's both academic institutions and also large IT companies trying to build these systems. Another very important aspect that gets used a lot in this general context of exploring quantum physics with superconducting circuits is the idea of cavity quantum electrodynamics. And cavity quantum electrodynamics studies the coupling of two-level systems to photons in resonators. And it was explored initially, say, with Rydberg atoms in 50 gigahertz microwave frequency resonators. And Serge Roche is one of the people who got a Nobel Prize for studies in this system. And these interactions at a single photon and single atom level were also looked at in atomic cavity QED with alkali atoms in experiments, for example, by Jeff Kimball and Gerhard Rempe and others. And then in the 2000s, in the early 2000s, the idea came about that one should use superconducting circuits to create cavity QED in these superconducting circuits to try to harness the coupling of superconducting qubits or superconducting artificial atoms to microwave frequency photons. And that is what created this field of circuit QED. And you can translate this top image here to the bottom one by thinking about having a superconducting nonlinear oscillator acting as a qubit or an artificial atom, coupling capacitively to a linear oscillator in which you store photons. And if this coupling is strong enough, you can convert quantum information from this nonlinear oscillator into the linear oscillator and back and use that for various interesting things. And one thing that I should point out is that since the middle of this week, or I think it was yesterday exactly, we have a nice review out on the archive about this idea of doing cavity QED with superconducting circuits, which turned out to be very useful in many different contexts. So what are properties of doing cavity QED with superconducting circuits? They provide strong coherent coupling in a solid state system. And it's really easy to achieve nowadays. You can more or less not avoid to build a strong coupling cavity QED system when you put superconducting circuits on a coherent electronic chip. It's also relatively simple to fabricate and integrate, and that's the reason why this is also used a lot in quantum information processing with superconducting circuits. And out of this idea, there's maybe three major directions that have developed. One is to do quantum optics experiments with superconducting circuits, where you look at the interaction of two-level systems with individual microwave frequency photons in the context of studying the interaction between these quantized systems. Then there's also experiments where you try to use these ideas of cavity QED with microwave frequency photons in circuits, also in hybrid quantum systems, where the hybrid comes from the fact that there's maybe other physical systems that have microwave frequency transitions, and that could be spins in semiconductors, hyperfine transitions in atoms, mechanical oscillators, magnons in magnetic systems, and many different systems can be explored with circuit QED in such hybrids. And then there's also quantum information processing, which is pursued. And so why is this in circuit QED in particular interesting in quantum information processing? So there's a number of reasons. First, you can put your superconducting circuit into strong coupling with a harmonic oscillator, and that allows you to isolate the qubits from the electromagnetic environment, because that allows to suppress the vacuum fluctuations of the electromagnetic field that the superconducting qubit sees, and thus enhance its coherence times, in comparison to just having the qubit in sort of free space. This can be done while maintaining addressability of the qubits, and you can also use this coupling of the qubit to a harmonic oscillator to read out the qubit state in a quantum non-diminishing way. And also you can not only couple a single qubit to a harmonic oscillator, but you can couple many qubits to the same harmonic oscillator. And that could then mediate interactions, and you can do 2-qubit gates between qubits in this way. And finally, you can use this coupling to convert excitations in this harmonic oscillator, in this qubit, to photons stored in a cavity. So there's these 5 useful features that circuit QED provides. I'll give you a few examples that I can just flash, and you can look at them more carefully later by either looking at the recorded video or asking me for the slides. So there's been really a nice range of quantum optics experiments that have been done with superconducting circuits that you see some examples of here. There have been many different hybrid systems that have been investigated, and I've mentioned them, and they also include NV centers and gate-defined quantum dots and mechanical oscillators and many more. And superconducting circuits have fulfilled all the DiVincenzo criteria, and therefore are currently pursued, as I said also in the beginning, for quantum information processing. And essentially all the elements are there, all the basic algorithms have been demonstrated, and now people look at real applications and look at realizing quantum error correction in these circuits. And while we're trying to push for error-corrected quantum computers in these systems, you can also use superconducting circuits for doing quantum simulations, either digital or analog ones. And there's really a vast range of applications that people have explored in very different areas of physics, and even exploring quantum chemistry, for example, thinking about simulating biological systems and exploring a wide range of different applications. And I think this shows that there's lots of activity in this field, and it's quite interesting, I would say. Good. So that would conclude my introductory part, and I hope you got a little bit of an idea on how superconducting circuits work, and what criteria you need to fulfill to investigate their quantum physics, and also what applications people look at, both for basic sciences and for quantum information processing. And so I will now spend the remainder of the time in looking at this idea of creating fault tolerance in superconducting circuits, or thinking about quantum error correction. And this picture we've looked at already in the beginning. Yeah, there's this set of data qubits and in red, and set of ancilla qubits in blue and green. Okay, here we see that set of qubits again. So in this particular example, there's 5 by 5 data qubits shown in red, so 25 in total. And then there is 24 ancilla qubits shown in blue and green. And these ancilla qubits fall into 2 different categories, namely so-called X and Z-type ancillas. And these different ancillas you try to use to figure out whether errors occur on the data qubits. And if you have X and Z types ancillas, they allow you to both look at amplitude and phase errors occurring. So both energy relaxation in data qubits, but also phase errors occurring in the data qubits. And the occurrence of an error in this surface code idea are trying to be tagged by using so-called stabilizer measurements. So these stabilizer measurements are relatively complicated measurements that you do on the 4 qubits that neighbor a specific ancilla qubit. So in this particular place here, you do a weight 4 Z stabilizer measurement. And what that means in particular, I'll explain in a second. At this, with these blue qubits, for example, you do a weight 4x stabilizer measurement on the 4 neighboring data qubits. And how these work, I'll tell you or what this means, I'll tell you in a second. But how do you perform such a stabilizer measurement between data qubits and an ancillar qubit is shown here in a quantum gate sequence. So the red dots are 4 data qubits, say the ones that you see here surrounding this green ancillar qubit there. And to perform this so-called stabilizer measurement, what it is that you do is you run a 2-qubit gate, like a CNOT gate, between every one of the data qubits and the ancillar qubit sequentially. And then at the end, you perform a measurement on the ancillar qubit. And then from that measurement, you can actually tell whether the parity of this 4 data qubits has changed during a period of time or not. And what that means, I'll tell you in a second. And you can do that in 2 different bases, namely in the Z basis for the green ancillar qubits. And you can turn that measurement into the X basis by performing a basis transformation on your data qubit. And the basis transformation is performed by applying pi half pulses to every one of your data qubit to go from, say, the Z into the X basis. Okay, let's and this is a core aspect of realizing quantum error correction, is to do these stabilizer measurements on the data qubits using the ancillar qubits. And for that to work well, all the elements that are required for it need to be working extremely well. So the individual qubit gates need to work well, the 2-qubit gates need to work well, and the readout needs to work well. And so that's listed in this list below here. And you essentially need to run this error detection circuit all the time while your quantum computer does error correction during its execution. So let's look a little bit at these parity measurements. So here's a simpler example only with 2 data qubits. So here the data qubits are blue and the ancillar qubit is red. So when both of the data qubits are in the ground state and you perform a CNOT gate between a data qubit and the ancillar qubit, if the data qubit is in the state 0, the CNOT gate tells you it does nothing on your ancillar qubit. So the ancillar qubit stays in 0. Oops, sorry. So when both of the data qubits are in the excited state, the CNOT gate gets activated and it flips the ancillar qubit first from 0 to 1. But then since there's 2 data qubits, the second CNOT gate will flip the ancillar qubit back from 1 to 0. So in these both cases, the ancillar qubit ends up in the 0 after this process. And so this gate sequence then shows you that it can identify the parity of the 2-qubit state. So here both qubits are in a 0 state, here both qubits are in the 1 state, and that means that both of these states are even parity states. There's equally many zeros and ones in these qubits, and the number of them is even. So that's an even parity state. So you could then identify an odd parity state in the same way. So if one of the qubits is in 0 and the other one is in 1, then only one of the CNOT gates will actually flip the ancillar from 0 to 1, and your ancillar will end up in the 1 state at the end. And this allows this sequence of CNOT gates to determine whether the parity of a multi-qubit state has changed or not. Yeah? When the ancillar remains in the ground state, the parity has not changed. When the ancillar switches to the excited state, the parity has changed. And that is the essential idea of these stabilizer measurements that one implements not only on 2 qubits, but on 4 qubits in this surface code. Good, so how does one do these CNOT gates in superconducting circuits? That's on the next slide here. So what you see here is 2-qubit states for, say, that could be qubit A could be one of your data qubits and qubit B could be one of the ancillar qubits. So interestingly, these superconducting qubits, while we say qubits to them, they not only have a ground state and a first excited state, but they have these higher excited states, you remember from all the states that sit in this cosinusoidal potential. And the gate that we like to use for this experiment here is one where we bring the state where both qubits, the data and the ancillar qubit, are in the excited state in resonance with a state where the data qubit is in the second excited state and the ancilla is in the ground state. And this resonance we can create by tuning the transition frequency of one of the qubits in a way that all the energy levels align such that 2, 0 and 1, 1 are in resonance. And when the two qubits have an opportunity to interact with each other, for example, through a resonator, that they're both coupled to each other, then this 1, 1 and the 2, 0 state will hybridize. And if you look at it in the time domain, this hybridization leads to a coherent oscillation between 1, 1 and 2, 0. So in the first half of the process, you would oscillate from 1, 1 to 2, 0. And if you wait exactly twice as long, you will be back to 1, 1. And quantum mechanically, what happens is that you create a phase factor in front of your 1, 1 state. And that's what you can use to create a logical C0 gate in this circuit. And this is conditioned only on the system being in the 1, 1 state. Namely, when you're in the 1, 0, 0, 1, or 0, 0 state, none of these states gets in resonance with anything else, so they don't acquire phase factors. And so once you've tuned the qubit back to its original frequency, only when it was in the 1, 1 state has it acquired this phase factor, and for all the other states it didn't do anything. And so the unitary matrix that corresponds to that is the one which has 1s on the diagonal and a -1 in this last spot here that indicates this 1, 1 state. And so this you can use to create a C0 gate, and you can turn this so-called C-phase gate that we use into a C0 gate in the following way. So in my circuit diagrams that I showed to you, when there's two lines that are connected by another line with two dots on them, that indicates a C-phase gate. What you then see in circuit diagrams is these C0 gates, which have a point on one of the lines and a plus sign on the other one of the lines. And you can turn such a C-phase gate into a C0 gate by adding two single qubit gates on one of the qubits. And when you do that, you can turn this C-phase unitary matrix into a C0 unitary matrix. So here you see the diagram for a C-phase gate, and you add 2 pi half pulses on the target qubit, and that turns it into the C0 gate. And the C0 gate has this unitary matrix that you see here. And you can then check whether that works or not by doing something that is called process tomography. And this here is a picture of such a process tomography measurement in superconducting circuits that we've done in our lab, where you can demonstrate that this gate that I've just explained to you works with fidelities that are around 99% if you are careful with it. Then in superconducting circuits, doing single qubit gates is rather easy. It works like doing single qubit gates in atoms and also in other systems. You use resonant microwave resonant radiation that links states in two different levels with each other. And so, for example, by applying a microwave pulse to such a single qubit, you can bring its Bloch vector from the north pole to an equal superposition state, and then applying a pulse that is twice as long, you can bring the system to the south pole, doing a pi pulse, or doing a 2 pi pulse, you bring it to the north pole. And the points on the surface of this Bloch sphere here are actually measurements, and on the right-hand side you see animations that represent the single qubit density matrix and also the single qubit Pauli operator expectation values. And you can perform these single qubit rotations about two different axes. You perform it about the one axis when you choose one phase of your microwave pulses that you apply to the system. And you can do the rotations about a different axis by changing the phase of the radiation that you apply by pi half. And then the qubit will rotate about the y-axis, as you see here. And on the right-hand side, you see the dynamics in these measured density matrices. So that's the way how you do single qubit gates. Then one thing that our lab is particularly good at is doing fast and high fidelity single shot measurement of superconducting qubits. And maybe I'll not explain that in a lot of detail, but what we've been able to do is to reach about 99% readout fidelity on timescales that are around 50 nanoseconds or a bit longer. And we've looked at that problem quite carefully, and I think we still have the the best readout performance from anyone in the area, including IBM and Google and others who work on this question. And this readout is particularly important for implementing surface code and error correction, because there you need to read out your ancillar qubits all the time. So maybe I say only one thing about how this readout works. So here's a blue curve, which is a spectrum of one of the resonators that we use for readout. And there's a red curve, which is the spectrum of the same resonator, but now with the qubit, rather than being in the ground state, the qubit is in the excited state. And what you see is that the state change of the qubit leads to a frequency shift in this resonant feature in the resonator. And a readout of this frequency shift allows you to actually determine the qubit state from such a measurement. And that's what we do, and that can work with this 99% fidelity or even better. Okay, so now I've told you about all the elements that you need, how you do 2-qubit gates, single qubit gates, readout, and now you can put everything together in realizing this surface code. So unfortunately, currently doing this surface code with 49 qubits is a bit difficult for us. So we're focusing on the simplest element that you could think of that still is a surface code. And that's a surface code with 7 qubits. You see there's 4 data qubits here in red and then 3 ancillar qubits. And what that allows you to do is you can actually detect whether errors occur on these 4 data qubits, but you can't correct for them. And that's why this is an error detection protocol and not an error correction protocol yet. So what is it that we do? We do this stabilizer measurements. The 4 data qubits D1 to D4 get performed on an X stabilizer measurement with this ancillar qubit in the middle. And then D2 and D4 are performing Z stabilizer measurements with A3, and D1 and D3 do Z stabilizer measurement of weight 2 with the ancillar qubit A1. And then if you look into the maths of this, you see that all these stabilizers, they commute with each other. And therefore they have common eigenstates. And you can now choose these common eigenstates to encode quantum information in this data qubits. So one way to do that is, for example, you could define a logical zero as an equal superposition between all the data qubits being in the ground state and all the data qubits being in the excited state. And you could go ahead and define the logical 1 state as this particular combination where you have an equal superposition of 0, 1, 0, 1 with 1, 0, 1, 0. And if you look at that, both of these states are even parity states. So if you perform a parity measurement on them, you will find that they're both even. And your parity measurement doesn't tell you anything about whether you're in the 0 or in the 1 state. However, if there was an error occurring on one of the qubits, say the last qubit flips from 0 to 1, the parity would change, and your parity measurement would indicate that, and then you would know that an error had occurred. Okay, so you can not only do this logical ground and logical excited state, but you can prepare equal superpositions of these logical and states, create logical superposition states. And those fulfill the same criteria, and that's the reason why it's possible to measure parity without affecting the states of these logical qubits. And that's essential. You need to be able to identify whether an error has occurred or not by performing these measurements without getting to know the qubit state while you perform these parity measurements. So then you can also ask yourself how you can perform logical operations on such a logical qubit. And you can do phase changes using this ZL, logical qubit Z operator, or you can flip the logical qubit with this logical qubit X operator. So you can turn a ground state into an excited state by flipping the states of the 2nd and the 4th qubit, which is what this operator here does. And that lets you go from 0 to 1, for example. And these, like usual, these logical operators on the logical qubit subspace, they then anti-commute with each other, as you're used to for the in the usual case when you consider a physical qubit. Good, so then we're sort of ready to go ahead. So here's our 7-qubit device that you've seen in the beginning. I've told you already what the different elements are, so I don't need to go through that again. We can put our red dots on it and see that there's these 4 data qubits, D1 up to D4 in a square geometry. And then there's 3 ancillar qubits that sit in between there, and we've just explained what they do. So this chip that you see here on this slide, that then gets put into a sample mount, and that's a sample mount that we've designed and then made at ETH. This is the chip that the experiment was actually done on, and you send signals towards the chip through these little connectors. You put the whole thing into a package inside your cryogenic system, and this is, you see that's a hand of a person, so the package is not particularly small, maybe 10 centimeters or 15 in diameter. And then you put this sample mount into a cryogenic setup to achieve these low temperatures, which we've mentioned are important to make sure that the system remains in the ground state rather than being thermally excited. Yeah, here you see some of the elements that go into this cryogenic system. There's lots of shielding, IR shielding, magnetic shielding, many filters and many things. And if you're interested in the cryogenics of it, you can look at this paper that we have published last year. And then you buy yourself a bunch of microwave equipment from your favorite equipment manufacturer, and you hook that up to apply microwave and current pulses to your qubits to perform gates along the ways that I've explained to you just before. Good, so here's some specs, like the fingerprint of our device. There are 7 qubits on it, the 4 data qubits, 3 ancillar qubits, and here you see their transition frequencies. So they're somewhere between 4 and 6 gigahertz. And here's coherence parameters, which are on the order of 10 microseconds. So this is not particularly good. Maybe the best devices in the area have maybe around 100 microsecond coherences these days, but it's still quite respectable. And what is special about this chip is that the readout fidelity and the readout time is very, very good. So overall, this is maybe not the most spectacular device that you've ever seen, but it has very well-balanced performance, and that allowed us to do the best possible quantum error detection experiment so far. Yeah, and again, I should stress that this readout performance is really essential, and I'll point at it in a second again. Good, and one of the aspects that is important about readout, so maybe you remember that there were data qubits sitting in a square, and the ancillar qubits were sitting in between them. And while the quantum computer runs, you don't want to touch the data qubits unless an error has occurred. But you need to run measurements on the ancillar qubits that sit in the middle between the data qubits. And what is important, while you perform this measurement on the ancillar qubits, the data qubits can't be affected by that measurement. And that's, for example, something that is extremely difficult in ion traps to do, to perform measurements on a subset of the ions while not affecting the others. And this we've realized here very nicely. So we have a contrast between measuring and not measuring a qubit, which is better than a factor of 10 to the 4. And that's essential in our experiments. So then we've looked at how good the single qubit gates and the 2 qubit gates work in our device. So next to every dot, which is a qubit, you see the single qubit gate fidelity that we've determined using a technique that is called randomized benchmarking. The same randomized benchmarking technique we've used to determine the fidelity or the error of the 2 qubit gates, which you see on these links between the qubits. So those are a little bit worse, yeah? and you might think, okay, those need to get better in the future, but they were actually fairly respectable and made this experiment work. Okay, and then we were ready to do our experiment, and obviously nothing stands fully on its own in research ever. There's always things that relate to it that have been done previously, and error correction is obviously a field that's been investigated for quite some time. So there were different error correction codes that were implemented previously. There was some fault-tolerant quantum state encoding done previously. There's work on error correction not with qubits but with bosonic codes that is done at Yale and other places. And there have been experiments that demonstrated these weight 2 parity measurements and also state stabilization. And one of these experiments we've done also in our own lab. And our breakthrough in this particular experiment was that we now had the largest surface code that anyone has done so far. And we were able to do these weight 4 parity measurements. both in the X and the Z basis, and we were also able to repeat that multiple times, up to 10 times that we have demonstrated so far. And with that, we could actually, conditioned on the situation that no errors were detected, show that our encoding scheme creates qubits with a better coherence than the physical qubits that this encoding scheme is based on. And in the next step, you would try to go from 7 to 17 qubits to not only detect errors, but also correct for these errors. Okay, so how did that then proceed? We need to do these weight 2 and weight 4 parity measurements, which we checked that they worked. So the green qubits, the green ancillas do weight 2 parity measurements, and the blue ancilla does weight 4 parity measurements. And you see the quantum circuits that correspond to these 3 different ancilla qubits and the stabilizer measurement that needs to be performed. And one can check whether these stabilizer measurements work by preparing all the data qubits in any of the computational basis states. So here below you see a list of the computational basis states that we run this parity check on, or the stabilizer measurement on. And what we should see is that the ancilla should stay in the ground state when the parity is even, which is clearly the case for 0, 0 and 1, 1. Or for these weight 4 stabilizer measurements for all the ones with even number of zeros and even numbers of ones. And when there's an uneven number of, or an odd number of zeros and ones, then the ancilla should be in the excited state. And that's exactly what you see in this experiment. And you also see that it's not perfect because the blue bars don't reach to 1, but there's a small error on them. And you can look at how big the error is, and the error is for the weight 2 stabilizer measurements, maybe around 5 to 10%, and for the weight 4 stabilizer measurement, which takes longer because you have to do 4 gates, it's a little bit worse, so maybe slightly above 15% or so. And these stabilizer measurements then you can use in this error correction protocol, which is the last thing that I'll explain. So here you now see the gate sequence for this error detection protocol. There's again the 4 data qubits, the 3 ancilla qubits. They all get prepared in the ground state when you start the experiment. Then what you do in the first step is you perform an X stabilizer measurement with the ancilla qubit in the middle, so this blue one, the A21. You run these 4C phase gates on it. Because it's an X basis measurement, you need to rotate the basis of your data qubits. And so this gate sequence then performs maps the parity of these 4 qubits in the X basis onto your ancilla qubit. And then you measure your ancilla qubit state. And if it remains in the ground state, you know that no error had occurred. And if it was in the excited state, you know that there was a failure in the circuit due to decoherence or due to a gate error. And then in the second step, that you can actually start while your measurement on the first step still works, you do the parity measurements with the ancilla qubits that sit on the side. And these are Z basis ancilla measurements, so they don't require these basis changed gates, but only require these C phase gates. And then when that is over, you perform the measurement on the 2 ancilla qubits, and then you continue, you just repeat. And this repeating in the circuit we indicated in this musical notation with these repeat bars. And this circuit just wraps around and you let it run. And in an actual error-corrected quantum computer, this would run always and forever in the background to always detect for errors and then try to correct for them if you have enough qubits for doing that. And at the end, you can check whether your final state is the one that you expected it to be in a measurement. All right, so let's look at whether that works. So we could, we could start with having all the data qubits in the ground state and just run this circuit and see what happens. We run it once and see what happens. So if we start with everything in the ground state and we run it once, we see that we actually prepare our fault-tolerant logical qubit ground state, which is this GHZ state, this equal superposition between 0, 0 and 1, 1, 1, 1, 1. And so we can look at that by just performing tomography on our 4 data qubits at the end of the circuit. So here you see this tomogram, which has the features of a GHZ state. And you could look at the fidelity of that. Yeah? And it's pretty decent, but not spectacular. It's 70% fidelity. But this fidelity you can decompose in a probability to actually be in the logical substate. and then the fidelity of the logical subspace. And when you project this density matrix into the logical subspace, you find that within that logical subspace, the fidelity of that logical state is 98.2%. And when you now start with with the data qubits in different initial states, what you find is that you prepare the different logical qubit states, either the ground state, the excited states, or equal superposition states between the logical qubit states. And so this shows that when you apply the circuit once, you can prepare all the relevant logical qubit states, including their superpositions. And then the final step that you do is, like, once you've prepared such a logical state, either one of the basis state or an equal superposition, you continue to repeat your error detection cycle and measure what the final state is. And so that's shown in this graph here on the right-hand side, both for preparing the logical ground state and for preparing the logical excited state. And at the bottom here, you see the number of cycles, the number of times that you've repeated the circuit that is between the repeat bars on the last slide. And on the top, you have kind of the wall time in the lab. And what you see is when at the end of the circuit, you measure the ground state probability or the excited state probability, you see that the temporal decay of that is slower than the temporal decay of the best of one of the qubits, of the physical qubits in your 7-qubit surface code. And that shows that running this error detection cycle increases the coherence, the logical qubit lifetime, to about 62 microseconds in this case. And this shows this for the basis states. But you can do the same thing for superposition states. And so the same measurement here is done for superposition states, and it's repeated. And you look at how it decays, and from the decay you can evaluate the logical coherence time, which is a bit more than 70 microseconds in this case. And the best physical energy relaxation times were 17 microseconds and coherence times were 22 microseconds. So we get something like a factor of 3 improvement in performance by running this error detection code. And what is important to say in this case, this is error detection. And so what happens is, like, every time that you detect an error, you discard the data because you can't correct for it yet. And why, I can maybe say something in the questions about. What is maybe important to notice is, as you go through cycles, every cycle you detect that some errors have occurred. And formally, the probability should be roughly 50% of the cycles should show an error. And then if you have 10 cycles that you do, your probability of having had no error is getting very small. And in our experiment, after 10 cycles, the probability of having had no error is about 10 to the minus 4. So it's tiny at that stage. And that's one of the reasons why when you implement error correction, you need to be able to kind of actively act against these errors or take note of them throughout running the circuit. And what we've also looked at is with what likelihood an individual error occurs or multiple errors occur. And we could analyze that in some detail and have a quite good understanding of the dynamics of our circuit and how our error detection circuit works. And we can really see that it performs as we expect. And we've also compared it to what we can learn from master equation simulation. And we were able to identify the dominant sources of error in these circuits. Good. With that, I'd like to conclude and say that we have demonstrated repeated error detection in the 7-qubit surface code. We've increased the logical qubit lifetimes and coherence times by maybe around a factor of 3 or so. And the main limitation currently is the individual qubit coherence. And the next steps would be to add more qubits to this, move from the 7-qubit quantum error detection to a 17-qubit quantum error correction in the surface code architecture. And with 17 qubits, you then have enough qubits that you get enough measurement, enough error syndromes that actually allow you to tell on which qubit the error did occur. And once you know that, you can actually correct that error. And then the next step would obviously be to reduce these errors to go below this threshold where you can then implement quantum error correction in a way that makes the error corrected qubit better then the non-error corrected one, and then you can think about doing gates between logical 2-qubit gates, between logical qubits, meaning doing a logical 2-qubit gate. An essential bit in this quantum error correction is also that you are able to do feedback. At some stage, once you've detected errors, you need to correct for these errors by acting on the qubits on which the error has occurred and flipping them back into the state that you desire. And that requires you to have a little bit of electronics that allows for feedback. And in a smaller experiment, we had shown that last year that we could do these parity measurements to, for example, stabilize entangled states. So technically, we're in principle able to do this short time feedback on these circuits. Okay, so with that, I'd like to wrap up, being a little bit over time, and start thanking our team at ETH Zurich. So this has the people that I've mentioned in the beginning, but it also typically has maybe 10, sometimes even 15 undergraduate students that work with us, and this is the team picture from last summer, and we had a bit fun with ourselves there standing in the sun next to the woods at the ETH Hungerberg campus. And with that, I'd like to thank you for your attention and take some questions, and advertise as usual that if you're interested in this type of work, we're always looking for excellent grad students and postdocs and also technical staff. Thank you very much.